Okay, so today we're going to be starting a new topic. This is topic 5. This is all about BJTs, bipolar junction transistors. We're going to spend 4 lectures on BJTs. What are we going to be doing this next 4 lectures? Yes. No? So first is today we're just going to be reviewing BJT models. So most of this information you already learned in EEE 123, and some of this information you learned in topic 2, when we took up BJT parameters in topic 2. But I'm going to be repeating this today. No? Baka sawa na kayo sa subject matter na to. I'm going to be repeating this. We want to emphasize these principles. And also, this is a good review, I guess, for your exam on Monday. No? Part of what we're going to be taking up today. No? So yun, no? We're going to start with a review of BJT models. Then we're going to go into BJT biasing. Biasing is setting up the operating point of a BJT when it is to be used as an amplifier. And then we're going to go into the BJT as an amplifier. We're going to be discussing the different topologies of BJT amplifiers. No? We used to spend only, I think, 3 lectures in this topic, but we decided that we would allocate an extra lecture this time because we want to be able to do uh, more problem solving with the students. No? Okay. Okay. So let me share my screen. Okay. Can everybody see my screen? Okay. Again, please give me a thumbs up. Okay. Okay, good. No? Okay, so again, what we're going to review today would be our BJT models. Okay, so this is what we're going to cover today. We'll discuss operating modes. We'll discuss active mode, large signal models. We're going to discuss saturation mode. And then we're going to go into collector characteristic curves. And then finally, we will discuss what we call the early effect. So actually, itong tatlong to, these 3 topics is really just a review. You took up some of these in EEE 123, and you also took some of these in topic 2 when we discussed BJT parameters. So you already know this. This has been pounded to you many, many times already. The operating mode of a BJT depends on the state of the base collector junction and the base emitter junction combined. No? So you have 4 possible combinations resulting in either cutoff, forward active, saturation, and reverse active operating mode. No? Remember that the reverse active operating mode is not really a useful operating mode. No? Usually you get into that operating mode only by accident. Okay, so let's review the current components in an NPN in active mode. So we took this up in topic 2. This was the second, I think, or third lecture of topic 2. No? We took this up in topic 2. First of all, no? Again, this is just a review. What is ICN? No? ICN is the collector current due to majority carriers. Okay. This is an NPN transistor. Do you remember what the majority carriers are in an NPN transistor? Can I have a shout out or a chat? What are the majority carriers in an NPN transistor? Anyone? Yeah, would appreciate participation. No? Anyone? Okay, that's right. Ano? Electrons. Electrons are the majority carriers in an NPN transistor. No? And therefore, what is ICN? ICN is the collector current due to electrons. Collector current due to electrons. Okay, we know that that is equal to alpha times ice of E. This, this component of your collector current, ICN, is equal to a factor alpha times ice of E, where we studied in topic 2 that alpha is equal to gamma multiplied by alphas of T, where gamma is our emitter efficiency, and alphas of T, we call this your base transport factor. So I recommend that you review what exactly is your emitter efficiency and what exactly is your base transport factor. Okay, so that is one component of your collector current. What is the other component of your collector current? The other component of your collector current is the reverse saturation current that flows between your collector and your base because it is reverse biased. So take a look at the polarity of your collector base voltage. The N is made positive with respect to the P, and therefore that is reverse biased. And therefore, what will flow is your reverse saturation current. This is a drift current, your reverse saturation current. So your total collector current is going to be ICN plus ICO. No? That's applying KCL at this point. So that is alpha ice of E plus ICO. No? Now we know if you treat this as a supernode, you know that ice of E, itong ice of E, the current leaving the transistor will be equal to the currents entering the transistor, which is ice of B plus ice of C. So we substitute that into this, and then finally, this is your expression for ice of C. But wait a minute, no? I have ice of C on the left side, and I also have ice of C on the right side, no? I want an expression for ice of C only in terms of alpha, ice of B, and ICO. So if I manipulate this equation, this is what is going to come out. No? Ice of C, ice of C is equal to alpha over 1 minus alpha ice of B plus 1 over 1 minus alpha ICO. Okay. Now, if I let beta equal to alpha over 1 minus alpha, and then I again manipulate this equation, I'm going to come up with this equation. So this is the complete equation for ice of C in terms of beta, ice of B, and ICO. This is the complete equation for ice of C. This one is the complete equation for ice of C in terms of alpha, IB, and ICO. Again, this is your equation in terms of alpha. This is your equation in terms of beta. Okay, now remember that ICO is very small, and therefore, at the end of the day, you can neglect it most of the time at least, so that you have IC is just alpha ice of E, so that's from this equation, neglecting ICO, so this one. Ito naman, IC is equal to beta ice of B, so neglecting this particular term. Okay, and this is the equation that you were very familiar with in EEE 123. Again, this is just a review. So you know this model. This is your transistor. This is your BJT as a current-controlled current source. And this is a linear model. Everything here is linear. No? Sorry. At least this part is linear. No? This is non-linear. But usually we can consider this to be linear if we analyze the base emitter diode using a piecewise linear approximation. So if we analyze this using a piecewise linear approximation, then this is a linear model. Okay, this is a linear current-controlled current source. And normally we use this in making DC calculations. Even this, using the piecewise linear model, usually that is accurate enough, or that is sufficient when just making DC calculations. Okay, let's now develop a more accurate model of your transistor. Okay. From Shockley's equation, we know that IE is proportional to e to the VBE over V sub t minus 1. That is from Shockley's equation. How can we say that? No? Well, IE, remember IE is the current flowing through this junction. IE is the current flowing through this junction. And therefore, it should follow Shockley's equation. It should be proportional to e to the VBE over V sub t minus 1. By the way, our assumption here is the ideality factor of the base emitter diode is equal to 1. Now, since IC is proportional to IE, okay, our proportionality constant is alpha. Well, remember that this is an approximation, because alpha IE plus ICO, no? But yeah, for all intents and purposes, negligible yung ICO, so we say that IC is proportional to IE, then IC should also be proportional now to this, no? E to the VBE over V sub t minus 1. No? It just follows, no? This is proportional to this is proportional to this, and therefore this should be proportional to that. Now, what is the constant of proportionality? The constant of proportionality is I sub S, which is the transistor saturation current, or we also call it the transistor scale current. Scale current. And the reason why we call it the transistor scale current is because that is a function of the size of the transistor. No? More accurately, it is a function of the surface area of the emitter base junction. No? It's a function of the surface area of the emitter base junction. So typically for transistors, that will be in the range of 10 to the minus 18 amperes to 10 to the minus 12 amperes. So notice, it is a very small value. So itong I sub S is a very small value. Now, since beta is equal to IB, if I compute for IB, that will just be IC over beta. So this is IC. No? That's IC. Let me be consistent with my. Just want to be consistent, no? With my case. No? So this is IC. So IB is just IC divided by beta. No? Sorry, kasali ito. IC divided by beta. No? And what is IE? IE is 1 plus beta over beta times IC. No? You learned this in EEE 1, 2, 3. No? So this is also IC. Okay, so those are the different current components in an NPN in active mode. Using the exponential model of your transistor, which is based on Shockley's equation. No? Now remember that under normal circumstances, ito, no, e to the VBE over VT is very much greater than 1. And so what does that mean? That means that under normal circumstances, we can neglect this minus 1. Okay, what about a PNP? So we've been talking about an NPN. What about a PNP? Again, we already studied this. No? My base emitter has to be forward biased. Since this is P and N, to forward bias the base emitter, the emitter has to be made positive with respect to the base. So this is now VEB, no? Instead of VBE. This is now VEB, the voltage from your emitter to your base. Now this has to be reverse biased. If this is to be reverse biased, your collector junction, then your base has to be made positive with respect to the collector. No? So that becomes VBC. In the NPN, it was VCB. So now it is VBC. So note the polarities of the voltages that we apply to make your PNP in active mode is opposite or are opposite the polarities that we apply for an NPN to make an NPN in active mode. Now, as a result, you will have currents that will flow, and your currents will now be opposite in direction to your NPN. So IE now will be inward, and IB and IC will be outward. Now, what are your majority carriers now? Now it is holes that are your majority carriers. No? Holes are your majority carriers. Okay. So when we talk, for example, about ICP, no? ICP is the portion of IC that is due to majority carriers, and that is holes. Now, the nice thing about a PNP, no, is that the direction of current and the direction of majority carrier flow are the same, unlike in the NPN. That's why in some books, no, it's the PNP that they study first because it's easier to visualize. Kung ano man yung direction ng majority carrier, yun din yung direction ng current flow. No? As opposed to the NPN, no, our majority carriers are actually flowing from your emitter to the collector. Remember, no? Your majority carriers come from the emitter, kaya nga siya tinawag na emitter kasi it is where the carriers are emitted, and that's why you call it the collector, because that is yun yung sumasalo, no? That is the collector of your carrier. So that goes from left to right. But if you take a look at the current, it will be from right to left because these are electrons, no? So that confusion does not happen in a PNP. Whatever the direction of flow of majority carriers, that also is the direction of flow of your current. No? Okay, so what do we have to do? We just have to swap voltage subscripts in the equations that we already discussed. So for example, if it's an NPN, this is supposed to be VBE. But now this is a PNP, so this is now VEB. No? VEB, VEB. No? These are the expressions for IC, IB, and IE. And you just have to remember that these are now opposite the direction of current that is found in an NPN. No? And under normal circumstances, VEB over VT is very much greater than 1. So these ones here can be neglected. Okay, so with that, we come up with a different model for your transistor. These are your Shockley-based BJT models. We also call this the exponential models of your transistor. No? Just like the Shockley model for the diode, we also call it the exponential model of your diode. So these are now the exponential models of your transistor. No? Unfortunately, this current source is no longer a linear current source. No? Because this is no longer a linear function of the variables in your transistor. Okay, this is, for example, this is no longer a linear function of VBE. Unlike our simplified model, which is a linear function of I sub B. So this is the NPN model. This is the PNP model. So again, take note, in the PNP model, we draw the emitter on top, the collector below. Okay, we're talking about the emitter-based diode here, which is forward biased. Okay, and okay, yeah, and this is your voltage-controlled voltage source, where this voltage-controlled current source, where this current source depends now on the value of VEB. So the emitter current is inward, the base current is outward, the collector current is outward. So when do we use this model? We use this mostly in AC analysis. You can use this in DC analysis if you want to have more accurate results. No? And if you know the parameters of your transistor, you can use this in DC analysis. But like I said earlier, in DC analysis, we usually just use the simplified models. Okay, if we're going to use this in AC analysis, then it might be that you would have to analyze your base emitter or your emitter-based diode also using the Shockley equation, or also using the exponential model of that diode. Okay. So this is the exercise that we did in topic 2. No? So I won't go through this anymore. We already went through this in class, actually. But I encourage you to review the solution to this problem because it's a very basic type of problem. Okay, before leaving active mode, are there any questions? Anyone? Any questions? Take advantage because this is also now like a review for your first long exam. Any questions? Active mode, no? We're only talking about active mode. Okay, there being none, let's go to the NPN transistor in saturation. What happens in saturation? In saturation, your collector-based junction is also forward biased. Remember, in active mode, in active mode, the emitter-based junction is forward biased, no? But the collector-based junction is reverse biased. No? But now, in saturation, both emitter-based junction and collector-based junction are forward biased. So take note. No? Earlier, this was VCB, the voltage from the collector to base, positive to negative. Now it is VBC, the voltage from the base to collector being positive to negative. Okay? What will happen? No? You're now going to have a forward current flowing in this loop. Okay? You will have a forward current flowing in this particular loop. No? Magkakaroon ka ng forward current dyan. The value of this current is IBC. How do you compute for IBC? Well, we can use the exponential model of the collector base diode to compute for IBC. No? That will follow Shockley's equation. So this actually is the characteristic curve of your collector base diode. No? It follows Shockley equation. You have IBC versus VBC, and that follows the equation ISC e to the VBC over V sub t, no? Assuming normal values of VBC. So this equation will work in this region, but this equation will not work in this region. No? Dito sa region na to, kailangan lagyan natin ng -1 because now this term will now be not much greater than 1. No? So again, remember, no? This equation will only work here in this region, but that will not work here. Kailangan ilagay natin yung -1. Okay? Okay, so what happens, no? When I compute now for IC, I have ICN, but I have to subtract from ICN this IBC. Okay, here. What is ICN? ICN is just my forward active collector current. ICN is my forward active collector current. So you can compute for ICN using your forward active relationship. That's I sub S e to the VBE over V sub T. Ito, no? Itong component na to, ICN, only really depends on VBE. No? Itong VBE. No? Okay? So you can still use this equation. No? Now, IBC, we already mentioned, is equal to this. So finally, this is your equation for I sub C. We can develop a circuit model from this, and this is our circuit model. When your collector base is reverse biased, then the current through this diode will be reverse saturation current. It will be flowing in the opposite direction. It will be reverse saturation current. It will be very, very small, that this is practically now an open circuit. So if this is an open circuit, what is this model? This is just our model. This is just our Shockley model for the transistor in forward active mode. No? Tanggalin natin itong diode. If we take this diode out, no? We can take this diode out when your collector base is reverse biased. But now this is forward bias, so now you have a current from your base to your collector through the base collector junction. Through the base collector junction. Okay? So what is IC? IC is this current minus this current. No? This is our model in saturation. Okay? So how does that affect IC with respect to VCE? When VCE is large, okay, VCE is the voltage from here to here, no? The voltage from here to here. So what does that consist of, no? VCE is equal to VBE minus VBC. No? So VCE is what? No? This is VBE minus VBC or plus VCB. No? If it's minus VBC, then that's plus VCB. Sige, iwan na lang natin yung VBC para hindi nakakalito. No? Let's just make this minus VBC. No? Again, ano? The voltage from here to here is this voltage. Now, this is opposite in polarity to this, so you subtract it, no? Minus this voltage. So that's VCE. Okay, when VCE is large, okay, VBE is more or less constant, no? Because we know that VBE will not deviate so much from 0.7 volts, okay, as long as the base emitter junction is conducting, no? Again, VCE is large, this is more or less constant. So what happens to this, no? This becomes, VBC becomes a negative number, right? Again, no? Malaki to, ito 0.7. This would have to be a negative number so that minus minus will be plus, no? Kaya ako ginawang plus kanina, no? I wanted to show this as plus, but okay. Sige, lagayin natin dito, no? VBE plus VCB, no? Plus VCB. Again, no? VCE is large, okay? VBE is practically constant, okay? So what does that mean? VCB will be large. VCB will be large. If VCB is large, no? Again, VCB opposite in polarity to VBC, that means this is reverse biased. And therefore, you are in active mode. What happens as you decrease VCE? No? Habang lumiliit yung VCE, no? As we're going in this curve toward the left. Okay, this remains practically constant, 0.7, thereabouts. Okay, if VCE is getting smaller, VCB will also get smaller. Okay, when VCE is smaller than 0.7 volts, VCB becomes negative. VCB becomes negative. If VCB is negative, ibig sabihin positive na ngayon yung VBC. Ibig sabihin, nagpa-forward bias na to. Okay? Again, ano? As we make this smaller, this becomes smaller. When this is 0.7 volts, or when this becomes smaller than 0.7 volts, this becomes negative. No? Or VBC becomes positive. No? Okay? So this becomes forward biased. And that's when this current will kick in. And when this current kicks in, that will subtract from our forward active current, and that's why this will go down. No? The value of your collector current will go down, and it will go down because of this term. No? Itong term na to, assuming that VBE is constant, this term stays more or less constant. No? Now this term will steadily increase as VCE decreases. So that's what happens. Now this is for one particular value of VBE. What about for other values of VBE? Well, for smaller values of VBE, you will have the following corresponding curves. So this is another value of VBE smaller than this one, another value of VBE smaller than this one, and another value of VBE smaller than this one. So you end up with these family of curves. Okay. Okay. So if you recall, in 1, 2, 3, we had a simplified way of analyzing BJTs in saturation. What was our premise for that? Okay, we said that the onset of saturation occurs when VBC is equal to 0.4 volts. So let me relate that to your base collector diode characteristic curve. No? So we already discussed this curve in the earlier slide. No? This is E to the VBC over V of T. Itong curve na to. Okay? When your voltage is 0.4 or less, then your current is very small. It is when your voltage exceeds 0.4 that the current starts becoming larger. So itong 0.4 na to, we call that your cut-in voltage, no? The cut-in voltage of your base collector or collector base diode. No? And then when you reach 0.5, okay, you have a substantial amount now of current. Okay. And even if you further increase that current, the voltage will no longer be substantially bigger than 0.5. Ano? In other words, a very, very marginal increase in 0.5 will cause a very large increase in IBC. But the voltage no, along this particular part of the curve, we can just approximate to be constant at 0.5. No? So 0.4 is our cut-in voltage. 0.5 is the voltage when it is well into saturation. Okay, actually all PN junctions have a cut-in voltage. When we say that silicon has a forward voltage of 0.7 volts, that means that the voltage across it when it is well into conduction is 0.7. But silicon diodes have a cut-in voltage. No? The cut-in voltage would probably be in the range of about 0.65 volts. Okay, so if VPE is 0.7, no? And we know that well into saturation, VBC is 0.5, VBE 0.7, VBC 0.5, then that means that the voltage across your collector emitter, which we call now VCE SAT, will only be about 0.2. So again, if you take a look at this from the perspective of the transistor, this is an NPN transistor. The voltage from here to here is 0.7. That's VBE. The voltage from here to here, no, from your base to your collector is 0.5. Itong 0.5 na to. Okay? And therefore, the voltage from your collector to emitter, ano yung matitira? No? 0.7 minus 0.5, ang matitira 0.2. So this is what you call your VCE saturated. For a PNP, you're looking at 0.7 from emitter to base. You're looking at 0.5 from collector to base. And therefore, what is left is 0.2 from emitter to collector. No? So this one is now VEC SAT. No? This is VCE SAT. This is VEC SAT. Again, no? Take note of the interchange. Take note that we interchange the subscripts. And so we came out now with this simplified model for the BJT in saturation, which we used in EEE 123, and which most of the time we will still continue to use here in EEE 131. What is the simplified model? Between your base and emitter, you just have VBE SAT. Between your collector and emitter, you just have VCE SAT. Here, it is from your emitter to base for the PNP, which is VEB SAT, emitter to collector, which is VEC SAT. Okay. Now, there's a caveat here, no? Because we say that a transistor is in saturation when both the emitter junction and the collector junction are forward biased. But remember that a junction can be forward biased but not conducting. So, for example, what if this junction were forward biased? That means the base to emitter voltage is positive, no? But not conducting. If the junction is forward biased but not conducting according to this model, then your collector current will be zero. So, strictly speaking, it is in saturation, no? Because both junctions are forward biased, strictly speaking. But if your emitter base diode, your base emitter diode is not conducting, then your current will be zero. No? That's why here I added the restriction that your base emitter diode must be conducting for you to be able to make use of this model. No? Same here. No? The emitter base has to be conducting for you to be able to make use of this model. So this is typically used in digital circuits and also in switching circuits. Okay. Are there any questions so far? Again, no? Are you still with me? If you're still with me, I'd like to see a sign. No? I'd like to make sure that I still have people listening rather than tuning out. Thank you. Thank you. Thank you. Okay. Okay, so let's discuss the BJT collector characteristic curves. I'm sure you've encountered this term before. No? When you say collector characteristic curves, we're talking about how the collector behaves, how the collector behaves. So what we're plotting is the collector current versus your collector to emitter voltage. Whenever we talk about the characteristic curves of any particular element, usually that's a plot of resulting current as a result of a voltage being applied. No? It's always current versus voltage. Just like the diode, if you remember the characteristic curve of the diode, the vertical axis is current and the horizontal axis is voltage. No? You have current flowing through your diode versus the voltage across your diode. No? So transistors are the same. You have current versus voltage. But in a transistor, no, the voltage VCE is not enough to dictate the current IC. No? As a matter of fact, in this particular case, it won't even affect the current IC. No? Let me explain that more later on. No? Okay, what else, what other information do we need to know to determine the current IC? No? In this particular case, we need to know the base current. We need to know the base current. Now, these are the characteristic curves of an ideal BJT if there were such a thing. If there were such a thing as an ideal BJT, the relationship between collector current and base current is just this. IC is equal to beta times IB. No? IC is equal to beta times IB. So note, no? This is IB. So for this particular value of IB, you have this value of IC, beta IB, and that is independent of VCE. Independent of VCE. In other words, the value of IC does not depend on VCE, it only depends on IB. So this is for IB3, which is greater than IB2, which is greater than IB1. Again, these are the collector characteristic curves of what would have been, or what we might call an ideal BJT. So we already know that the curve looks more like this. No? We already know that the curve looks more like this. Right? Earlier we showed this curve for VBE, no? But we can show the curve instead of with respect to VBE, with respect to IB. So this is the curve for IB1, the curve for IB2, the curve for IB3. We already discussed that when it is in active mode, IC depends only on IB. It does not vary with VCE. No? But when VCE becomes small, so that your collector base starts to become forward biased, then we already saw that IC will decrease. IC will decrease because of that factor ISC e to the VBC over VT. No? So this will decrease. Okay? Decrease there, decrease there. And this is now your saturation mode. Okay? Okay. Itong part ng active mode, no, sa totoo lang, hindi talaga to flat. This is not really flat. No? So it's not exactly accurate that ISO C does not vary with VCE in active mode. No? So here we're supposed to be in active mode. No? It is not exactly accurate that the current IC will not vary with VCE here, no? Because what actually happens is this has a slight slope. No? The dotted line is the actual. It has a slight slope. And the reason for that is this. No? As you increase VCE, you are increasing VCB. No? Again, as you increase VCE, you are increasing VCB. No? I think that is clear in, where did I show that? Saan ko ba pinakita yun, no? Dito sa slide na to, no? As you increase VCE, you will be increasing VCB, no? Because remember we said VBE is approximately constant. So pag ito lumalaki, itong VCB will be increasing, no? If that is increasing, okay, the reverse bias across your collector base is increasing, what will happen, ano? The potential energy drop from your base to your collector will become bigger. Remember that this is your built-in potential plus your reverse bias. No? So remember this value, this is VBI, no? Plus VCB. Right? Your built-in potential plus your reverse bias. What will happen if I increase VCB? Lalaki tong potential energy drop. No? So this is the potential energy profile E of C for electrons. Lalaki tong potential energy drop. No? And as a consequence, liliit, your effective base width becomes smaller. No? What is your effective base width? The effective base width is the width of your base excluding the depletion regions. No? The effective base width is the width of your base excluding your depletion region. This is the area in your base that your charge carriers from your emitter recombine. So remember, no, if this is an NPN, what do you have? You have electrons going this way. No? You have electrons. Ano nangyayari dito? There is some recombination. Right? But before all of these electrons can recombine, most of it would have fallen down this potential energy hill already. No? Most of these electrons will find its way to the collector. No? But here, in the base, in the effective base width, you have some recombination. Ngayon, kung mas maliit yung effective base width, you will have smaller recombination, and therefore your alpha will be larger. No? Your base transport factor will be larger. If your base transport factor is larger, your collector current will be larger. And that is the reason why, as you increase the reverse bias, your collector base, your current becomes increasingly larger. No? Of course, the difference could be negligible. No? The difference could be negligible because here we only show a very, very slight increase. This is what we call the early effect. Yan yung tinatawag nating early effect. We have to adjust our expression for I sub c to compensate for early effect. So our old expression for I sub c was just this. This is for your NPN. Just this term. Now we want to compensate for early effect. We add this particular term. This particular term shows now that I sub c will not only be dependent on VBE, it will now also be dependent on VCE. So I sub c now becomes dependent on two things, VBE and VCE. The greater the value of VCE, the greater this term, the larger the increase in I sub c. Again, let me repeat that. The greater the value of VCE, the larger this term, the greater the increase in I sub c. So we're seeing the increase. Okay. So that is for an NPN. For a PNP, it will now increase depending on VEC. Remember sa PNP, this is VEB and now this is VEC. Okay, I'm introducing here a new constant. Itong VA. What is this VA? What is this VA? That VA, we call that the early voltage. The early voltage. That is roughly the point of intersection of the collector characteristic curves with the negative x-axis if these curves were extended toward the left. Again, let's go back to these curves. So these curves would actually have a slope. And it just so happens that as IB increases, the slope will also increase. So this will have a slight slope. This will have a slightly bigger slope. This will have a bigger slope than the previous. So as you go up, your slope will increase. If I exaggerate these slopes, so I will exaggerate these slopes. Ito ang lalabas. So this is highly exaggerated. The slopes are actually very subtle, but let's just exaggerate it. Okay. So these are your active regions here. And then this is your saturation region. Now, if we extend this line, extend this line, extend this line, extend this line, they will all seem to converge at a certain point. And that point is the negative of your early voltage. This point is minus V sub A, the negative of your early voltage. And that voltage will typically be large, anywhere between 50 and 100 volts. Okay, let me ask, maybe just to wake you up. What is better, a small early voltage or a large early voltage? Anyone? Shout out na lang, Shout out na lang. Anyone? What is better, a small early voltage or a large early voltage? No? Anyone? Nahihiya kayo mag-shout out? Okay, I have somebody that tried to answer a small. Thank you very much, to John and to Chloe, for attempting to answer. Unfortunately, the answer is large, but I'd like to commend you for trying to answer, The answer is it's better to have a large early voltage. No? The reason is actually this increase, no, in IC, we don't really want that. We really want this to be flat. We want this to be flat. No, we don't want this slight increase. No, we don't like the early effect. No? If your early voltage is large, then this becomes small. This becomes small, and the increase in IC will be smaller. Okay, so we want the early voltage to be large. No, in other words, ideally, sana mas malaki yung early voltage. But thank you very much, no, to those two of you that to the two of you that tried to answer. Okay. Okay, so this is just an exercise, no? The transistor has a scale current of 5 times 10 to the no, ito, no? This transistor has a scale current of 5 times 10 to the minus 15 amperes and an early voltage of 50 volts. And then we assume it is operating at room temperature, no? Not here in the Philippines, but room temperature in temperate countries, 27 degrees centigrade. No? So question A, if V in is 4.32 volts, determine V out. Now, to do that, you would have to make an assumption on the operating mode of this particular transistor. So I'd like you to also validate that particular assumption. So the question is, if V in is equal to 4.32 volts, determine V out. This letter A is a problem that you should be able to solve from what you learned in topic 2. In other words, I'm not introducing anything new that will enable you to solve this problem. No? This problem is something you should be able to solve from what you learned in topic 2. No? Now, if you take a look at the UVLE notes, the exercise they gave is an NPN transistor. I changed it, no, in this particular session. I changed it to a PNP because you have to start familiarizing with yourselves with analyzing circuits with PNP transistors. No? In the real world, may NPN at saka may PNP. Kailangan pareho niyong kabisado paano mag-analyze ng NPN, paano mag-analyze ng PNP. Okay, I'm going to give you 10 minutes to do letter A. You can chat me your answer, and if you get the answer right, I'm going to give you some recitation credit for that. No? So, yeah, gawin niyo yung letter A, no? Yun yung una. Again, no, you don't need any of the information that I just introduced to be able to compute for letter A. Okay? So I'll give you about 10 minutes and then we will discuss the solution. Remember, this is not an NPN, this is a PNP. Okay, somebody very quickly got the answer, no? Because actually, pindot lang naman ng calculator talaga, no? Letter A lang tayo, ha? Letter A. Okay, I've several people already that got the correct answer. Yeah, I'll give you a few more minutes for people to try to solve it. Please try to solve. Huh? Okay, that's it. No? We don't have any more time, so let's just try. Let me just do the solution to this for the benefit of everybody that wasn't able to get it. Ano? Although I'm happy that most of you, or well, at least most of the ones that answered actually got the correct answer. No, um, again, no, this is something that you should have been able to solve using what you learned in topic 2. Okay, so okay, what equation do we need? No? What equation do we need? We need to use the exponential model of the transistor because that is what is given. No? What is given is your scale current. Okay. So when what is given is your scale current, that's already a hint that the model that you're going to use is the exponential model. No? So letter A, no? What is my equation? My equation is I sub C is equal to I sub S e to the, now remember, this is a PNP. So what will I sub C depend on? It will depend on V E B, no? So this is V E B over V sub T, no? Actually, may minus 1 dito, but we can just neglect this, no? Because for sure, with the voltages applied, no, this will end up being negligible. Okay, what is VEB? Anyone? What is VEB? No? VEB is equal to 5 volts minus V in, right? VEB is just 5 volts minus V in, no? And value of V in is 4.32, so I'm going to get VEB is equal to 0.68 volts. No? And therefore, I sub C is just going to be equal to 5, 10 to the minus 15, e to the 0.68 over 0.026. And if you do that, the answer that you're going to get is 1.1414 MA. 1.1414 MA. No? So simple lang. Okay? Simple lang. No? Nothing difficult about this particular problem. Yes, that's right. Ano? Two people answered correctly kung ano yung value ng VEB. No? Okay, hindi pa tapos yung problema natin because the question is determine V out. No? What is V out? No? If this is IC, right, this is the collector current flowing, V out is simply equal to IC times 1K. So this is in MA, you multiply it by K, nagka-cancel out. So you're just going to get 1.1414 volts. Okay. Now remember, you want to validate, because remember, this is only if it is in active mode, no? So this assumes active mode. No? So to validate, what do we have to solve for? No? To validate, you solve for VEC, no? Which is equal to 5 volts minus V out. No? So that is equal to, in fact, I don't have that figure. Let me do it. 3.86 volts. No? Note that VEC is greater than VEC sat. No? And therefore, your transistor is active mode. No? Active mode is confirmed. As long as the emitter to collector voltage is greater than VEC sat, then your active mode is confirmed. No? Okay. Any questions? Any questions? Okay, so another chance for some of you to get recitation points. Gawin ninyo yung letter B. Do letter B. Yun, no? Letter B, you now need material that I introduced in this particular lecture. You know? In particular, letter B, what did we say? No? IC now will be a function of both VEB and VEC. No? So IC will be equal to IS e to the VEB over V of t minus 1. And then meron tayong 1 plus VEC over V of A. Practically already told you how to solve the problem. One of your classmates kanina pa, no? Doon sa tanong ko sa letter A, sinagot na yung letter B, no? Correctly. Okay, that's it, no? I think I shouldn't accept any more answers. Um, Tama na, no? The correct answer is 1.199 volts, or essentially 2 volts. No? Halos lahat kayo nakuha, no? Okay, sige, no? Just so for the sake of those that didn't get it, although ang dami, no? Most of you actually got it, no? So remember ito, that's already negligible, no? We already know that this is we already know that this is 1.1414 MA, no? Okay. Now we know that IC is V out over 1K, no? IC is equal to V out over 1K, no? Okay. And we also know that VEC, ito, what is this? VEC is equal to 5 volts minus V out. VEC is 5 minus V out, no? And then V out is equal to, and IC, this is IC, no? Itong IC is V out over 1K. So if you take a look at this equation, you only have one unknown. No? Your only unknown is V out, no? V out is your only unknown. And this is not a nonlinear equation. No? You know this value, 1.414. This is linear. This is linear. Okay. So you should be able to solve for V out directly. No? I'm guessing yung iba sa inyo, tinamad, you probably even used your shift solve, but you don't have to use your shift solve to solve this. Ano? You could easily have used um, arithmetic. No? Not even algebra. This is simple equality. No? Anyway, if you solve for V out, you're to get V out is equal to 1.99, sorry, 1.1993, no, volts. Let me just make this. Okay. Any questions? Okay, so that's actually all that I wanted to discuss today. No? Okay, there's a question, no? Sinabi dito, no? Mr. Kirk, no? Recompute the value of V out if V in is 4.32 volts and an early voltage of 75 volts must be taken into consideration. So the early voltage that you are provided here is 75 volts, no? Hindi 50 volts. Okay? So this should be 75 volts. No, in A, bakit hindi ginamit sa A? No, in A, I told you to solve A. Hindi mo alam na may early effect, no? Sa letter A, in effect, I told you to solve it the way you would have solved it without knowing about early effect. No? In other words, um, basically disregard the early effect. No? Yun yung sa A. Okay, by the way, no, if you notice, this is with early effect, this is without early effect. If you notice, the difference is only about 0.05 volts. So V out with early effect is larger by about 0.05 volts than V out with early effect. No? So there are instances where you can really neglect early effect, basically. Any other questions? Okay, so like I said, this is all that I wanted to discuss now. Actually, we didn't have time. No, normally I would have moved on already to the next topic. No, which is to introduce the transistor as an amplifier. We already did a little bit of that, so 1, 2, 3. No, but now it's going to be more comprehensive. No, so good luck in your exam on Monday. Please study very well. Okay, I'm going to stop sharing now. And what I'm going to do is this, no? I will stay on for as long as there's someone that still wants to ask any questions, no? So the people that don't have any questions, they may leave. If somebody wants to ask me any question, they may stay. I will close the session when wala nang mga tanong. Okay? So okay, that's it. Thank you.